people who are just watching it online don't get to hear that whole conversation?
No, I'm actually that bothers me because I didn't mind. But well, whatever. I just forgot to hit play or record or whatever I was supposed to hit. Like I just work here. We've already covered that. I don't know what's going on. All right. So homework assignment. We were supposed to. What were we supposed to do? Oh, deal cards into the players' decks, right? Okay. And actually, interesting thing here. Let me. Well, we'll write it normally first, and then I want to find out if how a certain thing works in Blockly. So what we need to do is we already have our deck filled up. So we fill our deck up here. Then we shuffle the deck. We actually already know how it works because shuffling the deck does make the changes, right? So now what we can do is we can say deal. So I'm going to write a function up here called deal. Okay. Deal cards. And deal cards is going to take in, oh, this way, a player, and a deck. So P1, P2, and a deck. All right, so that's what the deal cards function needs to do its thing. All right, so what we're going to do is we're going to do something 26 times. Or we can do it until the deck is empty, but we happen to know the deck has 52 cards in it, right? So if we're going to do something some number of times, we're going to repeat 26 times. What are we going to do each time? We're going to give a card to the player 1. So we're going to say we're going to set player 1's, let's say last element, equal to a card from the deck. So that is get from deck first element.
Don't you need to get and remove it? That way.
Is there a get and remove?
I think it's under get.
There we go. Get and remove first element. So that's what we'll do for player 1. This is what we'll do for player 2.
I think you have to change the set too, what we found out, because otherwise it just kept changing the last card to maybe not.
I don't think it should. Well, we'll find out here in a second. All right, so this should be all you had to do for the homework. You didn't have to put it in a function like this, but I did. It'll be easier. So we're going to deal the cards, repeat something 26 times, give player 1 a card from the deck. So we're going to add to player 1's hand. Actually, hold on. This isn't right yet. Because player 1 is a player object, right? A player list. We really want to get the second element in his list, and that's the guy we want to add the card to. So really we need to say get from the list player 1 the element at position 2. Because remember when we built a player here, player has a name, a hand, and the cards that they've won. Okay, if you want to treat these guys backwards, that's fine. You can say cards that you won in your hand. But so this is 1, this is 2, this is 3. So we're getting this list. So that is player 1's list at position 2, and we're setting that list equal to a card from our deck. So I'm going to steal this whole thing. Put that here. We'll dump this, and this is from player 2. All right, so now we're actually dealing cards to player 1's hand, player 2's hand, and we're setting the last card in that equal to a card that we're removing from the deck. Make sense? Okay, so now down here in our game, we can now call deal cards, passing it our 3 things. So we just built our players. Now we're going to go ahead and call deal cards. And we're going to pass it player 1. I'll just steal this guy. Pass it player 1. Player 2. And our deck. Which we call the deck. So after this point in time, our cards should be filled, right? So deck should be depleted. Player 1 should have 26 cards. Player 2 should have 26 cards. All right, so let's start off by just printing the length of those 3 lists, just to see if they have the number of things in them we think they should have in them. So we're going to go ahead and we're going to print. The length of in list player 1 get position 2. That's his deck that we filled. All right, so the length of that particular list, then the length of player 2's list, then the length of the deck, which is a list in and of itself. All right, so we're hoping we get 26, 26, 0 as our answer. So let me go ahead and just copy this. All right, that's unfortunate. So does this not do what I thought it was going to do? I thought I could put that in a function, because didn't we shuffle our deck here?
Yeah.
And then didn't we print it out here?
Shuffle. You know.
Let me do something real quick. I want to print the deck outside of here. I thought we had done that last time. Or did we print it inside of shuffle deck? We may have done it inside of shuffle deck. We'll find out here in a second. For each item, I enlist the deck. We're going to print, actually we're going to call display card, right? And the card we're going to display is I. So this should give us 52 cards. The hope is jumbled up. If they're not jumbled up, then that means that our function up here to shuffle the cards doesn't do what we intended it to do. It shuffles them, but it doesn't have a permanent effect outside of this, which is actually okay. That just tells us something of how Blockly works. Wait a minute. Oh, that actually tells us quite a bit. The deck is an empty list. Then we're going through, we're filling the deck up with cards. Then we're shuffling the deck. Let me, what row? After I shuffle the deck, let me print it. That would indicate that shuffling the deck actually empties the deck. Oh, there's the King of Diamonds, Ace of Hearts, Four of Hearts. All right, that guy shuffled, right? Okay, we're good.
I think it might be the set the last, because we tried to do that and we had to change it to insert at last.
Oh, that actually is right.
Because it just kept changing the last one.
All right, there we go. So this dude up here, so instead of set,
We need
insert at last. Yep, that makes sense. So let's take our print off so we don't have to print the whole deck. And now we should have 26, 26, and 0. All right, good. Although, interestingly, why wouldn't the other with the set, why wouldn't the other two lists have one element in them?
It's weird.
Because even though we just kept overwriting the last element, the last time we overwrote it, there would still have been one card in there.
Yeah.
I don't know.
52 cards or something?
No, we definitely have 52 cards.
Yeah.
Okay, well, let me just explain what I was hoping was going to work there, and it did. Is notice that I passed here in deal cards. I passed these local variables, player 1, player 2, and the deck. These are things that are kind of local to our main program here, this guy. In fact, actually, to take this one step further, what I'm going to do, and I meant to do this actually last time, I'm going to create something here called main. Okay? And main is going to actually hold our entire program. And then what we're going to do to run our program, we're just going to call main. All right? So even though it seems like the same thing, you know, it seems like it's acting like the same thing, there's a fact in computer programming, and this relates to the C programming language. And we maybe even mentioned it in here once, that all programs begin and end with main. Did I ever say that in here before? Okay, let me show you something here for some proof of that. So here's a Java program, and this is from 300. This is something you guys will be dealing with in a year. So pretty complex stuff that we're doing in here. A lot of code that you'll be writing. But you'll notice right back here at the beginning, this is the beginning of that program, we have a single method called main. So even though we have all of these lines of code throughout, we have what, 1, 2, 3, 4, 5, 6, 7 separate objects. The program begins and ends right here. So our program really is 4 lines of code. And behind these is all the magic. Okay, this kind of gets back to how object-oriented programming works. We talked about the telephone example way back when, where we know there's a bunch of details inside the phone. Those details are housed in these guys. We're just looking at the telephone. So we're creating something called a parser. That's our telephone. Then we're telling that parser to parse, telling our telephone, make a call. We're getting the connection from the call. This returns the thing called the syntax tree from it. And then we're just printing it out. So really only 4 things happen. Modern programming languages begin and end with main. So every single one of them will have this main method. And the reason for that is they come from a much, much, much older language. So let me show you that. Let's see here. Just open another terminal. CD desktop. Do I have a blah dot C somewhere out here? I don't have a sample C program. Oh, whatever. So we're going to write a C program. So this is really old. This is an old school programming language. Remember we looked at that chart? We had C, the C programming language, way at the top. So this is what C looks like. So we're going to have and include H int main int arg C char pointer arg V. Okay, so punchline here being we see a main method. This language came from like the early 70s. Been around for a long time. So I can compile this now, blah.c, and there's my hello world program. Okay, C has a main method. C++ has a main method. Java has a main method. Android applications, which is still Java, will have main methods. C#, Swift, they all have main. They all begin with main. All right, so to kind of drag that into our Blockly model, even though we can just throw everything out there in general, just throw it out there in the middle of the world, by throwing it inside of a function called main and then just calling that one function, we're more closely emulating how modern languages work. Kind of make sense? Okay. So hopefully this guy still works. There's our 26, there's our 26, and there's our 0. All right. So we'll always just call main at the end. So here in our main deal here, now that we've dealt the cards, we need to actually play the game of war. Right? So let's write that function. What does play the game of war mean? It means the players go head to head, back and forth, and continue to compare their cards to each other. Correct? Well, we need to be able to compare cards. So we need a function for comparing cards to see who wins. So let's create a function. And this function is going to be called compare cards. And compare cards is going to take in two cards, C1, C2. Okay, remember we implemented our cards as two-element lists, right? We have a display name and we have a value. So where's our... well, actually, we don't have a value. That's okay. So what we need to do is we have this thing where our cards have display values 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. When we're playing war, does a 2 beat a 3? No. The higher number wins. 10 versus Jack. Who wins? Okay, Jack versus Queen. So what's Jack's numeric value? 11. What's Queen's numeric value? 12. King is 13. Ace is 14. So numerically, that's how we compare. Now in war, we don't deal with suits for so Ace versus Ace, regardless of suit, that's war, right? So really, we're going to have to add one more layer to our cards when we build cards. A card is not just a display value and a suit. It's now a display value a suit, and an actual value. That is, actual values would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're going to add a third element to our cards. So I'm actually going to steal this guy. We'll put it up above. Let's see. We're going to create a new variable, and we're going to call this the actual values. Okay, and the actual values are actually going to have a whole bunch of numbers in there. And where do we create a card? Let's build player, or whatever. All right, and we're going to get numbers to throw in there. So value 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Go ahead.
Shouldn't this just be a big logic statement of if two cards are equal, then it's print war.
That's if they're, so we could say if their display values are the same, then we know we're going to war. But we first need to compare their display values or compare their values. So if we have two cards and we have a 3 versus an 8, we need to be able to say that the 8 is actually better than the 3. And where we run into problems is when we get to the king, queen, jack, ace, those guys. Because those don't have numeric values associated with them. That's why we're giving numeric values. All right. Now, the reality here is that while this was almost palatable, almost, we don't want that. Bad news bears. All right. So what we're going to do instead is we're going to create a variable called the actual values, and we're going to set the actual values to initially be an empty list, and then we can create a loop that counts from 2 to 14. Then in list the actual values, insert at last, I. Won't that do it? No big deal. All right. Similarly, we've decided we hate this. Our display values. So we're going to set our display values to be a make list from text with delimiter. What else can I do here? Oh, text from list. I just go the other way. Make list from text, and then I'm just going to throw some text in here. 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. A little bit more compact. And we could have done the same thing up here, but we really wanted these to be numeric. That's why we created the loop and filled it with numbers. Similarly, suits, this isn't so bad. You can almost kind of say one or the other. So we could probably leave that guy alone. What the heck. This is hearts, clubs, diamonds, spades. So that'll fill up that list. So that compressed things down quite a bit, didn't it? All right, so do you see kind of the advantage now of using loops and some of these built-in power tools to do some of these things? All right, so now we have actual values, display values, and suits. Then we create our deck, and this guy here, his job is to fill the deck. Okay, so what we're doing is we're saying for every suit name, every display name, what are we doing? We're saying in our deck, we're going to insert at the last position, we're going to create a list with display name, suit name, and now we also need to give it a. Okay. But we have an issue. Where am I going to get my actual value? Display name and suit name came from these two things here. Suit name we know is going to go through 4 times. So for every suit name, we're good there. But would you agree that display value and actual value have the exact same number of values in them? So it would be beneficial for us to go through those numerically so that when we go to actually build our card right here, we'll pass it a display value. We'll pass it the suit name, which we have. But the display value will be display values get the value at a certain position. Actual values will be get the values at a certain position. So we'll have numeric access to it. Okay, so we're going to change up this loop just a little bit. So we'll count from I to the length of, we can choose either the actual values or the display values, because both of those guys have the same length, correct? Step by one, what do we want to do each time? We want to do this type of thing. Except display value is not a variable that we have right now. Instead, what we need to do is we need to get an element from a list. So in list, where is my display values? Oh, was it? It was there? Well, that's display value. Somewhere we should have the display values. Oh, no, we don't. I need to rename this. the display values. You could name it whatever you wanted, but just to stay consistent with what we were doing. Here's the display values, here's the suits, here's the deck, and here's the actual values. Okay, so now we'll say in list the display values, get element at bucket J. Similarly, in list, we need to add one more element to this guy. Here, we'll put our suit name. Actually, we want to put our suit name in the middle. That way we don't break our display. The display assumes the suit is in the middle, or suit is at bucket 2. So at bucket 3, we're going to put our actual value. Make sense? So now a card is a little bit more complex than it used to be. It's now 3 elements: a display value, a suit name, and an actual value. And we can use that actual value to compare 2 cards. All right. Copy this XML. So now, comparing 2 cards. We have C1 and C2 is going to get passed into this function, and all we're going to do is we're going to return whether or not, well, we'll decide how we're going to return, but we're going to initially determine, is C1 greater than C2, or is C2 greater than C1, or are they equal? Okay? So we need to ask a question. If we know that C1 is greater than C2, if C1's actual value is larger than C2's actual value, and C1's actual value is bucket 3 in its list. Correct? So we're going to say if in list, what list? C1, if that guy at position 3 we want to ask if that's greater than the same dude at position 3 in C2. So we're going to need more logic. Here's our greater than. If this dude is greater than C2's actual value, if that's a true statement, what are we going to do? Well, let's go ahead and we're going to return something here. So we're going to create a variable, a local variable. And just for our mentality, I guess, let's say that we're going to create a variable called the winner. And the winner is going to start off as the empty string. No winner. And the winner is going to either be first, second, or tie. First being the first card you passed in, second being the second card you passed in, tie being it was a tie. So if the first card beats the second card, we're going to set the winner equal to first. Okay? Else if the second card beats the first card, winner will be second. Else, winner will be tie. Finally, we're going to return winner. Okay? So compare cards takes in two parameters, a card and another card. It goes through and checks the cards against each other. If the first card beats the second card, set winner to first. If the second card beats the first card, set winner to second. Otherwise, set winner to tie. Return that value. Make sense? Okay, so that's compare cards. As we go through our game of war, we're going to have to keep comparing cards. What cards we're comparing? Well, we have two players. Player 1 will take his first card. Player 2 will take his first card. They'll pass it into compare cards. Depending on what compare card sends back, player 1 or player 2 knows who won. If player 1 won, that is if compare cards returns first, then what he'll do is he'll add those cards to his winning deck, so bucket 3 of that guy, and move on to the next one. If player 2 won, meaning that compare cards return second, player 2 will add those cards to his winning deck. If it's a tie, then what do? You burn 3 cards, right? Everybody puts 3 cards out. And then you compare the 4th card. Is that accurate? Is that how Game of War works? So we all throw 3 cards into the pot. That's the potential winnings right there. So now both people have 4 cards into the pot. So there's 8 cards there. Then they throw an additional card. Now there's 10 cards in the pot. And it's that last card that we compare. If it's tie again, then we throw more cards into the pot. Make sense? So for your homework, write play war. And this guy should take in 2 players and a deck. Oh, let me give these guys some names. Player 1, player 2, and a deck. Make sense? All right, final homework assignment of the semester. Next class, we'll come back and we will solve this, and then we'll talk about what to expect on the exam. Sound good? All right. Make sure, this assignment's probably a little more challenging than the last one, but it's not as bad as it might sound. Make sure you're using Slack to ask questions. A lot of students are, and you're getting pretty quick responses, I think, and some students are getting together helping each other. So I encourage you to use that.